Good day and welcome to your mathematics live class. Now, over the course of our knowledge or journey into calculus, we have been looking at various kinds of concepts as regards calculus and in terms of how to calculate using calculus. We talked about the concept of differentiation as the first branch of calculus, where we looked at differentiation of different kinds of functions, whether it's the algebraic function or the logarithmic function or the exponential function, or in fact different other kinds of functions which are included in the trigonometric functions. We also looked at ways in which we could extend all those preliminary differentiations into differentiating product of those functions. We looked at the product rule, which serves as the rule for differentiating products of functions, as well as the quotient rule, which is the rule for differentiating divisions of functions. We then moved further away from that into discussions into first principle, which serves as the explanation of the preliminary process that goes on while we are carrying out and calculating differentiation and differentiation factors that we have. Today, we'll be beginning the next bit of business under calculus. We will now be moving towards the second branch of calculus, which is known as integration. Now, remember or recall that we talked about the fact that differentiation and integrations can be defined as reverse processes of one another. Whatever differentiation does, you can use integration to reverse that process. Similarly, whatever integration does, you can also use differentiation to reverse the process. So it's a case of reversals or anti in terms of both of them. Differentiation one side, integration as the mirror concept on the other side. These are the two ways in which we carry out the processes of calculus. Now, for today's class or for today's lesson, we are going to be extending that concept into this mirror image of the differentiation we have already talked about, and that's the concept of integration. Now, just as we began differentiation by differentiating various kinds of functions, we are also going to pick that same route for integration. We are going to be integrating first, as a preliminary case, the integration of functions, different kinds of functions, as the case might be. The very first function we are going to put in our list is the concept of the integration of algebraic functions. So we are going to begin first and foremost with the algebraic function. Now, while integrating algebraic functions, while carrying out the integration of algebraic functions, just as we did in the differentiation case, we also have to look at what the generalized form looks like. Now, in differentiation, we differentiated using this symbol. For integration, we'll be using this symbol. That's the very first similarity or distinction that exists between them. So let's put it out in full glare. Consider the general form of an algebraic function given as y is equal to ax raised by n. Then the integral of y, in this case, will be equal to the integral of ax raised by n. Now, just as we differentiated with respect to the independent variable, we also integrate with respect to the independent variable. So we are integrating this with respect to x. Now, how do we carry out the integration here? For algebraic functions, the integration of algebraic function simply picks to the power. Now, when you integrate, the constant is of no significance, actually. So you could bring out the constant first, because for the integral symbol, it has no dealing with the constant. All you need is that independent variable, just like when you have it in differentiation, and then all you need is just that independent variable. And then when you integrate, remember a is outside, integration of this will now give us an addition of 1 to the power and dividing by that original power. Then the addition of a constant. Now, this is a very, very important concept as far as integration is concerned. We must always, without exception, add the constant value whenever we complete an integration process, provided the integration process is of an indefinite integral. We are going to be looking at what that concept means shortly. But integrals where there is no symbol or sign attached to the integral is called an indefinite integral. We have what we call definite integrals that have what we refer to as bounds. We have that those bounds are put into what we call definite integrals. We are going to be looking at those integrals in detail as well. However, let's consider the generalized case, which is the indefinite integral. Whenever you integrate using this kind of integrals, then it is customary for you to put in a constant. Now, you'd wonder that with the addition of this, won't we have the tendency of ensuring that, this would now be different if we try to differentiate this function? No, that won't arise. The reason why that will not arise is the fact that if you differentiate the constant, you'd have 0. So differentiation of this constant will still give you 0. And then if you differentiate this, remember, by process of algebraic differentiation, n plus 1 will multiply a. Then, of course, you subtract 1 from the power. But that n plus 1 will divide this n plus 1. So it goes out. So you have ax raised to power n left, which still balances out the equation. That's why we call the integration a kind of reverse process for what differentiation is. This is the generalized form. Let's pick various examples as to how we can use this generalized form. First, let us integrate the following. Let's integrate 3x squared. Let's integrate 4x raised to power 5 plus 7x. Let us also integrate 2x squared plus 3x plus 6. Let's have ourselves do this. Let's begin. We will begin with the first one. Integral of 3x squared dx. Do not forget, this is very, very essential. Again, by the process, the coefficient comes out. Integral of x squared dx, so that we can write this as 3. When you integrate an algebraic function, you add 1 to the power, and you divide by the new power. That's a concept. And do not forget your c. So at the end of the day, 2 plus 1 is 3, cancels out this. You would have x cubed plus c as a final result. Let's do the second one. We'll have the integral of 4x raised to power 5 plus 7x dx. One thing you have to know is just as the differentiation symbol is an additive function, the integration symbol is also an additive function. What does that mean when I say additive function? It means that I can integrate 4x raised to power 5 dx plus the integral of 7x dx. This is what it means to be an additive function. So I can bring in the integral into the sum. Now, integrating this, again, I will have 4x raised to power 6 divided by 6 plus, now, do not make the mistake of saying, okay, I've integrated this plus c, then I integrate this plus c. There's really no point to do that. Why? Because if you were to put in a constant here, and then you put in a constant here, if you add two constants together, you'll still get a constant. So we add in the constant only at our final result. And that's very, very important to note. We put in our constant only at the final result. So we integrate this as well. We have 7x squared divided by 2. Then we put our plus c. So you can simplify if you wish. This would give us 2x raised to power 6 divided by 3 plus 7x raised to power 2 divided by 2 plus c. This is how we complete this particular process. Then let's move on to the third one. We have to integrate 2x squared plus 3x plus 6 dx, right? So I'm sure you'd have already put in some attempts to solve this. Let's wait some 1 or 2 minutes while you attempt to solve this question, and then let's see using the format of what we have already done if you'll be able to attempt it correctly. All right, I'm sure you have worked through your own answers. Let's take this together and see what we have. Again, we can split this as an additive function, 2x squared dx plus integral of 3x dx plus integral of 6 dx. Interesting. And then, again, the constants can come out, plus 3 integral of x dx plus 6 integral of dx. Now, you might wonder, I have integral of dx there. There is no variable. How then do I solve that? Do not forget that if I have integral of dx, it's the same thing as saying integral of 1 dx, right? And then 1, how can I rewrite 1 in terms of the variable? Do not forget again that I can rewrite 1 as x is equal to 0 dx. So whenever you see integral of dx, just assume it's x is equal to 0 dx. Just as simple as that. And then we integrate. If you integrate on this side, we have 2x cubed divided by 3 plus 3x squared divided by 2. Adding 1 to the power divided by the new power. Add 1 to the power divided by the new power. And then here you have 6x, add 1 to the power, you have 0 plus 1. Divide by the new power, 0 plus 1 plus c. So at the end of the day, you have 2 over 3x cubed plus 3 over 2x squared plus 6x plus c. Simple and straightforward. So this is how we solve integration of simple algebraic functions. But does that mean that this is the only way, or this is the only kind of algebraic functions we can have? Not exactly. We can have different other kinds of algebraic functions. Let's delve into those other kinds. So this is 1. Let's take it 2. This time, we will look at what happens when we wish to solve integrals of values that are fractional. Integrate the following. So we would look at fractional powers, more fractional powers, then we'll look at something very interesting. Let's try to solve this and see exactly what we'll have. First question, integrate root of x. I'll have the integral of root of x dx. I can write root of x by my knowledge of indices as integral of x raised to half dx. So that if I carry out the integration process, I'll have x raised to 1 over 2 plus 1 divided by 1 over 2 plus 1 plus c. Simple. And then I'll have 1 over 2 plus 1 will give me 3 over 2. It's in a divided position, so it becomes 2 over 3, reciprocal, x raised to the power of 3 over 2 plus c. And if I was to write it in root form, I'll have it as 2 over 3 square root of x cubed plus c. Simple and straightforward. This is how to solve with fractional powers. So just express the fractional power as an indices, then integrate as you will. Simple and straightforward. You do not need to do anything more than that. Next, let us pick the second one. We are to integrate the cube root of x squared dx. This can be written as the integral of x raised to 2 over 3 dx. And then I integrate that, I have 2 over 3 plus 1 divided by 2 over 3 plus 1. I've integrated to not the dx anymore, it now becomes plus c. Then 2 over 3 plus 1, that gives me 5 over 3. So reciprocal wise, that gives me 3 over 5. X raised to the power of 5 over 3 plus c, which is also the same thing as 3 over 5. The cube root of x raised to the power 5 plus c. Simple and straightforward. So you do not need to fear if you have a fractional power. What if you have negative powers? So you have to integrate x to the power 5 plus 5x squared plus 3 divided by x squared dx. So before you start thinking of anything so large or so complex, remember that you can still split this. How do I mean? Remember your LCM, if you have 2 plus 6 here, you can always split it as 2 over 5 plus 6 over 5. By concept of LCM. So we can do that same thing there. So it means that if I want to split, I can easily split this as integral of x to the power 5 over x squared plus 5x squared over x squared plus 3 over x squared dx. Right? And then remember the integral is an additive function. X to the power 5 divided by x to the power 2. Law of indices, that gives me 5 minus 2, which is 3. So I have the integral of x cubed dx plus x squared will cancel here, plus the integral of 5 dx plus the integral of 3 divided by x squared can be written as 3 x to the power minus 2 dx. Again, using the concept of law of indices. Simple and straightforward. And then now I have a negative power. If I integrate this one, I'll have x to the power 4 divided by 4. Then here I'll have 5x, we have explained why. And then here, you have a negative power. It doesn't still change anything. You are still going to go through the process of adding 1, minus 2 plus 1 divided by minus 2 plus 1 plus c. So now you would have x to the power 4 divided by 4 plus 5x, then plus minus 2 plus 1 gives you minus 1. So it means that the sign will become negative. So you have minus 3x to the power minus 1 plus c. And then you're done. If you feel more comfortable in the reciprocal form, apply law of indices, you'd have it as x to the power 4 over 4 plus 5x minus 3 over x plus c. And you're done. This is how to carry out integrations. So whether it's a fractional power or it's a negative power, doesn't really matter. You can still solve them using the same process. What you have to watch out for is when your power becomes such that if you were to divide by the new power, you'll be dividing by a value of 0. That is something you have to be very, very careful about. And when does that happen? It happens when you integrate functions like this. Of course, you could write it by law of indices as x to the power minus 1 dx. But the moment you carry out the same process of algebraic integration, and then you add 1 to this power, you have minus 1 plus 1, which is 0. But then you have to divide by the new power. So it means you have to divide by 0. But then the moment you divide by 0, what happens? You get an undefined function, which means that we cannot approach solving this integration by this method, even though it is in fact an algebraic function. This is one of the reasons why the methods of integration are considered much more robust and wide compared to the methods of differentiation. Because of the fact that a little change in the function can create an entirely different method as far as integration is concerned, makes it much more wide compared to what is covered under differentiation. For the entire bulk of differentiation, you could have standard differentials, you could have first principle, you could have product rule, you could have quotient rule, you could have chain rule, and here you are done. Then you put higher derivatives. No simple, no complex process there. However, for integration, the more you pick those functions, the more you find variants that would not satisfy the original function or the original way of integrating that function. Then you have to create a new method for integrating that function. That method joins the list, and then you have a new method and joins the list, and you have another new method and joins the list, and the list continues to go over and over and over again. This is why integration is considered much more wide compared to its counterpart, the differentiation method. Now, how would we solve questions like this? This would lead us to the second kind of functions we are going to be integrating. Now, the second function we're going to be picking is the function third, the logarithmic function. Now, recall from our foray into differentiations that when we did the logarithmic function, we differentiated the logarithmic function, and our answer ended up being a fraction form. So now when we want to reverse the process, we will start with the fraction form, and then the integral of that fraction form will be a logarithmic function. What exactly do we mean? Let's see. So, logarithmic functions. So, consider the general form for log resulting functions. So functions that will result in a log form look usually in this form. Y will be equal to the differential of f of x divided by f of x, or f prime of x divided by f of x. I'm sure this is a form that is very, very common, or that is very, very familiar with us due to our foray into the concept of differentiation. Recall that in differentiation, whenever we took the logarithm and we differentiated the logarithm, we said we will first and foremost differentiate the inner function and then divide by that original inner function. So here, for a function to be able to result into a log form when we integrate, it has to be such that the numerator is in fact the differential of the denominator. So it means that if I take the integral of y, it has to be equal to the integral of f prime of x divided by f of x dx, and my result will now be the ln of f of x plus c. Do not forget there is an absolute value, which means that you do not want to consider whether it's going to be a negative result or a positive result. So long as this is satisfied, the ln takes an absolute value of that function. This is how to integrate logarithmic resulting functions. A good example of that is the very first example we picked that led us to the distortions into log functions. Integrate the following: 1 over x, 2x plus 3 divided by x squared plus 3x. Five x is power 4 plus 2x squared, all divided by x is power 5 plus x is power 3 So let's solve these three questions and see what we'll have. We'll start with the first one. The integral of 1 over x dx. We said we can't use the normal algebraic method, even though it's an algebraic function. Even though all of these are algebraic functions, we can't use the normal method. Why? Because if we were to use that normal method, we'd have x to the power minus 1, and then by the time we add 1 to the power, we'd have 0. So we can't divide by 0. So we have to work around it. How then can we